Let's talk about one of the biggest, most mind-bending questions in all of science. See, we have these two incredible theories that describe our universe. General relativity, it handles the really big stuff. Stars, galaxies, the whole cosmic web. And then there's quantum mechanics for the super weird, tiny world of particles. They both work perfectly, until they don't. The moment you try to rewind the clock all the way back to the very beginning of the universe, these two theories just crash into each other, and all the math, it just completely breaks. So, what really happened before the Big Bang?
So here's how we're going to try and crack this thing open. First, we'll look at exactly why our best theories just hit a wall at the starting line. Then, we're going to jump into some incredible possible solutions, from rewriting the quantum rulebook itself to imagining a cosmic bounce instead of a bang, and even a universe that's kind of reborn every single instant. We'll even ask a truly wild question: is reality just information? And finally, we'll circle back to the great unsolved cosmic puzzle.
Okay, so let's set the stage here. Modern physics is basically built on two massive pillars. And look, each one has been tested over and over and proven right time and time again. The problem is, they describe two realities that just don't seem to get along.
On one side, you've got general relativity. That's Einstein's baby. It describes the universe on the grandest scales. Gravity, planets, black holes, the very fabric of space-time. It's literally the reason the GPS on your phone works. Then, on the other side, you've got quantum mechanics. This is the theory of the incredibly small, all the particles and forces that make things like lasers and computer chips possible. So you have two perfect theories, but for two totally separate worlds. And right here, this is the heart of the whole problem. The Big Bang forces these two theories into the same room. At that first moment, the entire universe was unbelievably small and dense, which means quantum rules were in charge. But it also had an unimaginable amount of gravity, which is relativity's territory. And when we try to use the equations from both to describe this so-called singularity, they just spit out nonsense. They give us answers like infinity, which makes zero physical sense. It's like we've hit a solid brick wall at the very beginning of time.
So, how do we get past this wall? Well, one idea is that maybe the theories themselves aren't wrong, but the rules we're using to apply them are. Some physicists are starting to argue that the standard version of quantum mechanics that you learn in textbooks, it's just not up to the job.
And that's exactly what physicist James Hartle thinks. He basically argues that the standard Copenhagen interpretation of quantum mechanics was designed for tiny, controlled experiments in a lab, but it makes some core assumptions that just completely fall apart when you try to apply it to the entire universe as one single quantum system.
So here are the two big issues. First, the standard theory says you need an observer to make a measurement to get a definite outcome. But, who was there to observe the Big Bang? Second, it's really good at predicting the future from the present, but cosmology is all about figuring out the past. Hartle's proposed solution is a totally new framework called decoherent histories, which can calculate the probabilities for the universe's entire timeline, no observer needed.
This brings us to another really cool idea, which kind of sidesteps the whole beginning of time problem in a completely different way. What if the Big Bang wasn't a beginning at all? What if it was a bounce?
The classic picture, the one you probably saw in science class, is the hot Big Bang. It's this idea that everything, all of space and time, just exploded out of a single, infinitely hot and dense point called a singularity. That point is the beginning.
But science has updated the story. The modern view suggests there was a period before that hot fireball. It's called inflation, and it was this insane exponential expansion from some kind of quantum state. So the bang that we actually see the evidence for in the cosmos, that's really the reheating event that happened after inflation was over. This neatly separates the true origin from the event we call the Big Bang.
So, what was this quantum origin? Well, this is where ideas like string theory come in. They suggest that space-time doesn't actually break down into a singularity. Instead, when things get that dense, new quantum effects kick in and create a kind of repulsive force, preventing a total collapse and causing a bounce. This would mean our expanding universe might just be the rebound from a previous universe that collapsed in on itself.
Okay, so what if we go even deeper? What if we question something we take for granted every single second? The whole problem of a beginning assumes time works like a straight line, just flowing forward. But what if quantum mechanics tells us that the very nature of time is not what it seems?
To really get this next idea, we have to talk about time. So let's start with a simple analogy from the everyday world.
Okay, imagine you're tracking a single billiard ball as it moves across a table.
You could represent its entire journey by taking a single snapshot of many different billiard balls, each one placed exactly where the original ball was at a different moment in its path. In our normal, classical world, a history over time can be perfectly mapped onto a single moment in space. Easy enough, right?
But, and this is a really big but, does that simple trick work for a quantum particle like an electron? The physicist Yakir Arahanov asked this exact question, and the answer he found was a hard no. And that changes everything.
You see, a quantum particle is different. It's connected to its own past and its own future in ways that a bunch of separate particles just aren't. You can think of it like it has a kind of hidden memory. The particle knows where it's been and it knows where it's going. And because of these hidden connections through time, its history contains way more information than you can ever capture in a single snapshot.
So the solution they came up with is absolutely mind-bending. To fully describe a quantum particle right now, you don't just need to know its past state, you also need to know its future state. This implies that both the past and the future are actively shaping the present. In this view, the universe isn't just evolving forward, it's being completely reborn every single instant with its entire history and future all encoded in that one moment.
And all of this, it leads us to what might be the most radical, most out there idea of them all. So far, we've questioned observers, we've questioned beginnings, we've even questioned time itself. So what if we question the very stuff reality is made of? What if the universe isn't made of matter and energy at all, but of pure information? This idea asks us to completely rethink what we mean by the multiverse. It's not about a bunch of parallel worlds living side by side. No, in this view, the multiverse is temporal. It's the infinite sequence of moments, every zeptosecond, that makes up the history of our one universe. The past, the present, the future, all existing together as one thing.
So in this framework, what is reality? It's fundamentally information. The building blocks aren't atoms and quarks, they're bits of data, maybe forming complex mathematical shapes. The expansion of the universe we see, that's an illusion. Instead, reality is static, but it's constantly refreshing itself, like a computer screen reloading so fast you can't see it. And if that's true, this constant regeneration could mean the universe avoids a final heat death and could potentially exist forever.
So, after all that, where does it leave us? Well, we've looked at these incredible and totally competing ideas. A universe with new quantum rules, a universe that bounces instead of bangs, one that's reborn every instant, and even one that's made of pure information. All of them trying to answer that one single question about the very beginning.
And I want to be clear, as wild as these ideas might sound, they aren't just random shots in the dark. They are serious, deeply mathematical attempts by brilliant physicists to solve the single biggest problem in their field, getting gravity and quantum mechanics to finally work together. Each one represents a possible path forward to a final theory of everything, from the tiniest particle right up to the entire cosmos.
And that really is the ultimate takeaway. To solve this puzzle, something fundamental about our picture of reality has to give. We might have to let go of the idea of a single moment of creation. Or we might have to abandon our gut feeling that time just flows smoothly forward. We might even have to accept that the universe isn't made of physical stuff at all. The only real question left is which one will it be?